Picture this. For nearly a decade, computer vision has been dominated by one architectural idea: the convolutional neural network. Convolutions bake in assumptions that feel almost obviously correct for images. Nearby pixels are related, patterns should be detected the same way regardless of where they appear, and features should be built up hierarchically from small local regions to larger ones. Meanwhile, over in natural language processing, a very different architecture called the transformer has essentially eaten the field, powering models like BERT and GPT. The transformer makes almost no assumptions about its input. It just treats everything as a sequence of tokens and learns relationships between them through self-attention. So a natural question lingers. Could you throw out all the carefully engineered vision-specific machinery and just apply a plain transformer to images? This paper, from a Google research team, gives a striking answer: yes, if you have enough data. To appreciate why this is surprising, consider what previous attempts looked like. Researchers had tried hybrid approaches, using convolutional networks as the backbone and sprinkling attention on top. Others tried replacing convolutions entirely with specialized attention patterns, but those required exotic engineering to run efficiently on modern GPUs and TPUs. The fundamental problem is that naive self-attention over an image is brutally expensive. If you treated every pixel as a token and let each pixel attend to every other pixel, the cost grows with the square of the number of pixels, which is hopeless for any realistic image. So prior work either confined attention to local neighborhoods, or used sparse approximations, or only attended along rows and columns separately. Clever, but none of it scaled cleanly, and convolutional networks like ResNets remained the undisputed champions on large-scale image recognition. The Vision Transformer, or ViT, sidesteps the cost problem with an almost embarrassingly simple trick. Instead of feeding pixels into the transformer, you chop the image into a grid of fixed-size patches, say 16 by 16 pixels each, and treat each patch as a token. A 224 by 224 image becomes a sequence of just 196 patches. Each patch gets flattened into a vector and passed through a learned linear projection that maps it into the transformer's working dimension. Think of it as building a small visual vocabulary on the fly, where each patch is like a word, and the linear projection is the embedding layer that converts these visual words into vectors. They then prepend a special learnable classification token to this sequence, borrowed directly from BERT. The idea being that this token has no inherent meaning at the start, but after passing through all the attention layers, it will have aggregated information from the entire image and can be used as the image's overall representation. Position embeddings are added so the model knows which patch came from where, and from there, it's just a standard transformer encoder. Alternating layers of multi-head self-attention and feed-forward MLPs, with layer normalization and residual connections. What's striking is what they did not do. They didn't use 2D-aware position embeddings, just standard learnable 1D ones, the same as in NLP. They didn't add any convolutional stem. They didn't bake in translation equivariance or locality. The model has to learn everything about images from scratch. The authors are explicit that this is a feature, not an oversight. They want to test whether the inductive biases of convolutions are actually necessary, or whether a generic architecture given enough data can learn the right biases on its own. And here's where the story gets interesting. When they train ViT on ImageNet alone, about 1.3 million images, it underperforms a comparably sized ResNet by a few percentage points. That seems to confirm what everyone believed. Vision needs its specialized inductive biases. But when they scale up the pre-training dataset to ImageNet-21K with 14 million images, ViT catches up. And when they pre-train on Google's internal JFT300M dataset with 300 million images, ViT pulls ahead decisively. The largest model, ViT Huge, with a 14-pixel patch size, hits 88.55% top 1 accuracy on ImageNet, 94.55% on CIFAR 100, and 77.63% on the VTAB suite of 19 transfer tasks, matching or beating the previous state-of-the-art from Big Transfer and Noisy Student, while requiring substantially less compute to pre-train. The smaller ViT Large pre-trained on JFT300M used about 680 TPU V3 core days compared to roughly 10,000 for Big Transfer and 12,000 for Noisy Student. The deeper insight here is about the relationship between inductive bias and data scale. Convolutional networks bake in strong assumptions which act like a head start when data is scarce. They don't have to learn that nearby pixels matter or that translation shouldn't change the answer. But these baked-in biases also impose a ceiling. The model can only do what its architecture allows. Transformers are the opposite. They start from near-zero assumptions but have enormous flexibility. With small data, that flexibility is a liability. With huge data, it becomes an asset because the model can learn richer and more flexible relationships than convolutions allow. The author's scaling study makes this concrete. On the performance versus compute frontier, ViT uses roughly 2 to 4 times less compute than ResNets to reach the same accuracy, and unlike ResNets, it shows no sign of saturating as you scale further. When they peek inside the trained model, the results are intuitive. The learned patch embedding filters look like plausible, low-level visual feature detectors, reminiscent of what early convolutional layers learn. The position embeddings, despite being unconstrained 1D vectors, organize themselves into a 2D grid structure where nearby patches have similar embeddings. The model rediscovers spatial topology on its own. And the attention heads, even in the earliest layers, show a mix of behaviors. Some attend globally across the whole image, while others stay narrowly local, functioning a bit like convolutional filters. As you go deeper, attention spans grow, and the model attends to semantically relevant regions for classification. The hybrid models, which feed CNN features into the transformer instead of raw patches, help at small scales but lose their advantage as models grow. Further evidence that pure ViT eventually learns whatever the convolutions were providing. Now, the honest caveats. ViT's strong results depend on access to enormous pre-training datasets, and the very best numbers come from JFT300M, which is proprietary to Google. The publicly accessible ImageNet-21K version is still competitive but doesn't quite match. The paper only tackles classification, detection, segmentation, and dense prediction tasks are left for future work. Self-supervised pre-training, which has been transformative for NLP, is only briefly explored here through a masked patch prediction task, and the gap with supervised pre-training remains around 4 percentage points. And while ViT is more compute efficient than ResNets at pre-training, the absolute compute required is still enormous, putting frontier results out of reach for most labs. Now let's walk through some questions you might have after hearing all of this. Why does splitting the image into patches solve the quadratic cost problem of attention? The issue with naive pixel-level attention is that the cost grows with the square of the sequence length, and a 224 by 224 image has over 50,000 pixels. Completely infeasible. By using 16 by 16 patches, you reduce that sequence to just 196 tokens, which is comparable to a sentence in NLP. The model gives up the ability to attend to individual pixels, but in exchange, it can run full global attention efficiently on hardware that's already well optimized for standard transformers. Why do convolutional networks win on small data but lose on large data? Convolutions hard-code two assumptions: that the same feature detector should apply everywhere in the image, and that information should be combined from small local neighborhoods first. These assumptions are almost always correct for natural images, so they save the model from having to learn them. But they're also constraints. They prevent the model from learning more flexible patterns, even if the data would support it. Transformers have no such constraints, so they need to spend data learning what convolutions get for free, but once they've learned those basics, they can keep going and discover relationships convolutions could never represent. What does the classification token actually do, and why prepend it instead of just pooling the patch outputs? The classification token is an extra learnable vector added to the front of the sequence that doesn't correspond to any patch. As it passes through the self-attention layers, it gathers information from all the patches through attention, and its final state serves as the summary representation used for classification. You could alternatively average pool the patch outputs, and the authors mention this works comparably, but the classification token approach was inherited from BERT and keeps the architecture maximally close to standard transformers, which was a deliberate design philosophy throughout the paper. For large-scale recommendation systems, ViT's core lesson is directly applicable beyond images. The patch and attend recipe generalizes to any setting where you want to apply transformers to high-dimensional structured inputs without designing modality-specific architectures. User behavior sequences, for example, can be tokenized into chunks of activity, clusters of recent interactions, sessions, or feature groups, and fed through a standard transformer. The finding that inductive bias matters less as data grows is especially relevant for platforms with billions of users and trillions of interactions. You can probably get away with simpler, more generic architectures than the hand-engineered two-tower or sequence models common in production today, provided you have the scale to support them. More concretely, the patch embedding idea suggests a clean way to handle heterogeneous features in candidate retrieval and ranking. Instead of designing separate embedding tables and feature crosses for each input type, you could project diverse feature groups, user history segments, item metadata blocks, context features, into a common embedding space and let attention learn the relationships. The compute efficiency story also matters. ViT's 2 to 4 times reduction in pre-training cost versus ResNets at matched accuracy hints that well-designed transformer recommenders may be cheaper to train at scale than the increasingly baroque deep and wide architectures in production. Even before considering that pre-trained backbones can be fine-tuned cheaply for downstream ranking tasks. Exactly the transfer learning pattern that has reshaped both NLP and now vision.